The instrument you see here is a so-called cryogenic ion trap instrument. And it's in principle an ultra-high vacuum instrument that allows us to store and manipulate molecular ions. My name is Sandra Brünken, and I am an assistant professor in the FELIX infrared and terahertz spectroscopy group. I came to HFM at FELIX around 3 years ago to make use of the unique infrared free electron lasers that we have here at FELIX for my research. My research is a very interdisciplinary field between laboratory astrophysics and astrochemistry, and it's in the intersection between molecular physics, chemistry, and astronomy. So you might ask, what is astrochemistry actually? And I guess that a lot of you quite often look up to the stars at night. But what some of you might not know, that the region between the stars, what we call the interstellar medium, is actually far from empty. It is filled with huge amounts of gas and dust, and this material collects in what we call molecular clouds, and these are in fact the birthplaces of stars and also the planetary systems. So in astrochemistry, we would like to understand the chemistry happening in these molecular clouds. We know from astronomical observations that a lot of organic large molecules exist in these clouds, and we want to understand how they are formed. These molecules and molecular processes also govern actually the evolution of these molecular clouds, and are very intimately linked to the process of star formation and planetary formation itself. So we would also like to learn how complex can this chemistry be? Can we maybe form really large organic molecules that might be precursors to life? So maybe it all started in space. So in order to understand what is happening in space, we actually use experiments here in the laboratory to simulate some of the processes. And what I find personally very fascinating in this field is that we can look at microscopic molecular processes here in the laboratory to in fact understand macroscopic processes like the evolution of a molecular cloud light years away. And we can learn about this just from studying similar processes here in the lab. We determined the age of a molecular cloud in this way just by looking at molecular spectra, and I found this personally very exciting. One of the main information that laboratory experiments can actually provide us with is what we like to call the spectral fingerprint of a molecule. Each molecule absorbs and emits light at a very specific wavelength. And what we do here in the laboratory is that we actually obtain this so-called spectral fingerprint by using the intense radiation of FELIX on specific molecules. Once we have the spectral fingerprint, we can then actually go to a telescope and try to detect the same molecule then in space. This already gives us a very crucial information if you want so the inventory of molecular species in a specific molecular cloud. And with similar methods, by now up to 200 different molecules have in fact been detected in space. Another information or another aspect that is maybe even more important is to understand the chemistry that's happening in these molecular clouds. In fact, a molecular cloud has a very extreme conditions. So it's very cold, down to temperatures of minus 260 or so degrees Celsius, or around 10 Kelvin, and it is very dilute. So we only have around 10,000 molecules per cubic centimeter. That's something that can barely be reached with the best vacuum in a laboratory. So what we want to do is to study the chemistry actually under conditions simulating those in space. And we do this by using an instrument, as you see here. This is a so-called cryogenic ion trap instrument. And what we can do here is to study reactions between molecular ions and neutrals at temperatures that are also prevalent in space. And we do this actually by cooling the ions. We use a helium cryostat for this, but it's in fact nothing else than a fridge. It works the same as a fridge that you have at home, but it works down to temperatures of minus 269 Celsius. So by using this, we can study reactions, and we want to do this actually in a rather controlled way. So we want to study a specific reaction, and what we do is we start with a specific molecular ion. And so we know the mass because we, in this instrument, have mass spectroscopic detection schemes. But we can also learn about the structure of the specific molecule, again by using FELIX to record vibrational spectra of these molecular ions. And once we have that, we can compare it to calculations to really get the geometry, the structure of the specific ion. So that's already a very good starting point, but then we do the reaction at these cold temperatures in our instrument with a neutral, and then we might form a lot of different products. And these also have different mass, so that's easy, but they can also have different structures again. And we have now in the past years actually developed methods to probe the structure, again using the FELIX light, taking vibrational spectra of the products in situ, that means while the reaction is happening in our instrument. And this now gives us a really very powerful new tool to study a very fundamental, or to understand very fundamentally and complete the formation pathways of these specific reactions we look at, but at conditions that are also prevalent in space. And of course, in the long run, what we want to do is we really want to understand the formation pathways towards large organic species. And as an example, I want to say the polycyclic aromatic molecules that are very abundant in space. And they're also linked to a very fancy other molecule that has recently been detected, which is the Buckminster fullerene. And also they are linked to the formation of dust. So I talked in the beginning about molecules and also dust. So these larger species might grow into dust, and then the dust might agglomerate more until we maybe at some point form really a planet. And this is what we really would like to study here on a very small scale to start with, to understand the very big scales out in space.